All right, a couple things here, before the start of the lecture today, okay? First, I already sent out the email, okay? So if you are in Wednesday lab sections, okay, so please complete the whole experiment, okay? So today, okay, because of the next Wednesday we have no class, okay? And so because of the typical chloride the lab, okay, so that's this week lab, okay, so it's a relatively easy one, okay, so we used to just use 1 week to finish this lab, okay, so that's should be no problem, okay. And so if you are in Thursday or Friday lab section, okay, so you can make your own decision, okay. So you can finish the whole experiment this week, and then you don't need to come in next week, okay. Otherwise, okay, so I will still post the sign up sheet, okay, so you can come in next week for the boiling point, okay. Yeah, so that's a lab, okay. And so I'm still grading the exam, okay, so hopefully, okay, so I can get it done by tomorrow, okay. And today we should able to finish chapter 13, okay. And so quiz 5 will all cover chapter 13, okay. Quiz 5 will be on Monday, okay, so next Monday, okay. And I will also post the homework, okay, so probably this afternoon, okay. All right, okay. So if you have any question, can you just type in the chat window, okay? All right, so first, we continue study the different functional group and different the IR absorption, okay? So amide, okay, so so that's the also the carbonyl the containing functional group, okay? So amide, okay, so remember, okay, so has the amine attached to carbonyl group, okay? So amine, okay, so can be primary amine, secondary amine, even tertiary amine, okay? Just replace the hydrogen with the RQ group, okay? And so interesting for the amide carbonyl absorption, okay, so pretty low, okay? About 1630 okay, to 1690 per centimeter, okay? So normally speaking, the amide for the carbonyl group, okay, so the absorption should be around the 1700, okay, but amide kind of definitely below the 1700, okay. Also for amide, okay, so there are primary amide, secondary amide, and tertiary amide. How do we distinguish them? Kind of similar to amine, okay. So if it's a primary amide case, primary amide, okay, NH2, okay, 2 hydrogen, okay. So you should see 2 NH stretching, okay, 2 peaks, okay. So for the NH, okay, so one's kind of symmetrical, another kind of unsymmetrical, okay, and around like 3300 okay to 3400 okay, so this area, okay. So one example showed here, okay, so that's the butanamide, okay, so you see kind of 2 peaks here, okay, so 3000 okay, 3400 okay, so 2 peaks, okay. So if it's here the secondary amide, okay, secondary, okay. So there's only one NH, okay, so that's you also only see one peaks, okay, in this area, okay, only one peak, okay. Yeah, so for the amide you should see the carbonyl stretching and also the CO bond stretching, okay. CC NH stretching case. Yes, All right, and then for the secondary amide case, so only one peak case. So example showed for the benzenamide case. So methyl benzenamide case. So so there's only one H, okay, so NH, okay, so in this case here you should only see one peak, okay. So if it's a tertiary amide, okay, so tertiary amide has no NH, okay, so just a 2 RQ group, okay. So that's here you won't see any kind of the NH stretching, okay, so 0 peak, okay. So example showed here is this is kind of tertiary amide case, so there are 2 RQ group, okay, and then no NH stretching, but here you still see kind of CO bond stretching, okay. All right, and here, okay, so we already cover a lot of the carbonyl compound, okay. So you can see kind of carbonyl compound their carbonyl can CO bond stretching kind of actually show big difference, okay. So the highest one, okay, pretty much is the acid chloride, okay. Okay, so about like about normally about 1800, okay. And then next kind of the hydride, okay, acid anhydride. So acid anhydride kind of the two peaks, okay, one peaks about 1810, okay, another about the 1760s, okay. So yeah, that's a little bit unique from others, okay, because the other only show one sealed up on stretching, okay. And then followed by ester, okay. So ester has some of this kind of structure, okay. All right. So ester sealed up on stretching, okay, so around like the 1740, 1750, okay, yeah, something here, okay. And then followed by aldehyde, okay. Sealed up on stretching about 1725, okay. And then ketone, okay. Ketone a little bit lower than aldehyde, okay, so about 1715, okay. All right, and then following, okay, so it's carboxylic acid, okay. So carboxylic acid kind of just around like 1700, okay, 1710 something, okay. And then amide, okay, so amide has the lowest kind of sealed up on stretching, okay, so yeah. Below normally below kind of the 1700, okay, something 30s, okay, to 1790s, okay. All right, okay, so please write down this order, okay. So I can promise you, okay, so the in quiz 5 or maybe in exam 3, okay. So there will be a ranking question, okay. So I ask you kind of rank the company group kind of the IR stretching, okay, so with frequency, okay. So you'll need remember this ranking, okay. All right, here comes question, okay. So yeah, all of them have kind of the same sealed up bond, okay. Why they have kind of different kind of the sealed up bond kind of IR signal, okay. So that's the company, okay. All right, okay. So yeah, a reason for that kind of carbonyl group, okay, so has some the CO single bond factors, okay, so yeah, that's we learned in the previous class, okay, so yeah, you control the rest of the structures, okay, like this. Yeah, okay, so charge separation, okay, so yeah, I want to put the lone pair electron, okay, on, okay, it's just kind of show here, okay. All right, so we already know that for the sealed bond, okay, so should be around like 1700, okay, per centimeter, okay. And CO single bond, okay, because kind of weaker bond than sealed bond, okay, so yeah, it's the showed kind of low frequency, about kind of 1200 okay, per centimeter, okay. So that means if you have the more double bond factors, okay, so you have higher frequency, okay. So if you have the more single bond factors, okay, so then you have a lower frequency, okay. Right. So now we'll see what factor can influence the kind of CO double bond stretching, okay. So first, the electron withdrawing effect, okay, and also called the inductive effect, okay, and also resonance effect, okay. So these two play kind of opposite rules, okay. So if there's electron withdrawing group attached to the CO bond, okay, so we'll increase the frequency, okay. So that's actually kind of not hard to understand, okay. So just draw here. All right. So if you have kind of electron withdrawing group, okay, pull electrons, okay, in this direction, okay, pull it down, okay. So if you pull it down, okay, so then you have kind of last the CO single bond the factors, okay, and then you have kind of high frequency, okay. And another kind of resonance, okay, resonance because you can shift the electrons, okay. So what happens kind of for resonance, okay. You have some kind of the heat atom, okay. So for example, we have just label as A, okay. Lone pair electrons, okay, and let's rest this, okay, shift the electron like this way. And then you get here more CO single bond kind of factors, okay. And then that's lower the frequency, okay. And here are two examples, okay. So more specific kind of the ester and no the amide, okay, comparison, okay. Ester has kind of a relatively higher kind of frequency, and the amide we know that kind of lowest one, okay. So theoretically speaking, okay, so for both, okay, so have these two factors, okay, so we call the inductive effect, okay, and also resonance effect, okay. yeah, because the oxygen and also amine both electron withdrawing group, okay, and both have lone pair electrons, okay, lone pair electrons, okay, so lone pair electron adjacent pi bond, okay, with short kind of a resonance structure, okay, so yeah, similar like here, okay, and yeah, okay, so possible charge will be on this, and so yeah, how come the ester has a higher frequency than the kind of amide, okay? The reason for that is yeah, for ester, okay, so inductive effect play major role, okay, so yeah. So for ester, okay, so yeah. So inductive effect just kind of electron withdrawing effect, okay. Kind of the yeah, win over the resonance, okay. So that's why ester has kind of a higher frequency, yeah, ester yeah, CO amount, okay. But for the amide case, we are because the yeah, resonance effect kind of play major role, okay. Then kind of inductive effect, okay. So that's why S has the pretty low frequency, okay. Yeah, so that's just two effect, okay, keep in mind, okay. So withdrawing group, okay, so increasing frequency, and then resonance, okay, lower frequency, okay. And third, yeah, the effect kind of hydrogen bonding. Hydrogen bonding kind of lower frequency, okay. So that's the yeah, for the capacity, so capacity kind of only the yeah, carbonyl compound has the OH group, okay, can build up the yeah, hydrogen bond, okay. So yeah, that's why capacity kind of the yeah, carbonyl group kind of the yeah, showed around like 1700 kind of the yeah, stretching, okay. And then fourth effect actually kind of the yeah, about conjugation, okay. So that's actually kind of yeah, pretty close to the yeah, resonance effect, okay. So yeah, if CO double bond kind of conjugated with the yeah, some pi bond, okay. So yeah, this pi bond can be arcane or maybe can be the yeah, aromatic ring, okay. So that's a conjugation. Remember we learned kind of yeah, double bond, single bond, double bond, single bond, double bond, single bond, okay, alternating, okay. Then yeah, this the yeah, carbonyl the yeah, IR stretching will much lower than kind of yeah, the 1700, okay. So yeah, you can see here, okay. So yeah, if we CO double bond conjugate with CC double bond, CC triple bond, okay, so lower carbonyl kind of absorption by 30 to 40 yeah, per centimeter, okay. The example is yeah, for the yeah, this is the yeah, acetophenol, okay. So yeah, pretty much it's kind of ketone, okay. So ketone we know that the yeah, frequency about the yeah, 17 yeah, 20 k something, okay. So yeah, but here okay, so yeah, because yeah, this yeah, carbonyl group, okay, conjugated with the benzene ring, okay. So yeah, double bond, single bond, double bond, single bond, okay. And then the carbonyl yeah, absorption for in kind of yeah, 1685, okay. So that's much lower than 1700 1720s, okay. So that's the please keep in mind, okay. So yeah, occasionally you see some kind of peak here, the lower than 1700, okay. That's maybe also the yeah, carbonyl group, okay. So that's please keep in mind, okay. All right, and then we'll study the last functional group, okay. So it's IR spectrum, okay. So that's the nitrate compound, okay. So for nitrate compound, okay, the yeah, CO yeah, CN triple bond, okay, so yeah, absorption around like 2200 to 2300, okay. We do like this. $23 per centimeter, okay. And so this yeah, fall in the triple bond region, okay. How do we distinguish the CN triple bond from the CC triple bond, okay? So CC triple bond that's from alkyne, okay. So remember, okay, so the yeah, CC triple bond, okay. So yeah, it's about kind of 2100 to 2200, okay. So that's somehow lower than CN triple bond, okay. So by that, you should able to distinguish the nitrite from the alkyne, okay. So just kind of look at this peak, about 2200K, so or below 2200, about 2200K, so nitrate compound, below 2200K, so that should be the alkyne, okay. So that's how do you distinguish these two, okay. Right. Okay. So now a little bit do the comparison for all the carbonyl compound, okay. So yeah, we learn a lot of the carbonyl compound, okay. So yeah, they all pretty much have the carbonyl stretching, okay. So yeah, about here the 1600, 1700, or even 1800. Okay. So yeah, in addition to the sealed bond stretching difference, okay, so yeah, we can also look at other Fokker group kind of IR spectrum, okay, so distinguish them. Right, so we do one by one, okay. So yeah, for the ketone, okay, so yeah, ketone there's only the sealed bond, okay. So yeah, no special kind of other absorption, okay. And aldehyde, okay, so aldehyde very similar structure to ketone, okay, but aldehyde has kind of special kind of CH stretching, okay. CH stretching, remember, okay, so that's here the not regular CH, okay, so that's here the carbonyl kind of CH, this one. So two peaks, okay, one around the 2750, another 2850, okay, so very unique, okay. All other CH stretching won't show the so low, okay. And for the carboxylic acid, okay, so in addition to the sealed bond stretching, you should see kind of very broad OH stretching, okay, so about the 2400 to 3500, okay, so very broad, okay, so that's the very unique for the carboxylic, okay. And then for the amide, okay, so amide, you should see kind of NH stretching, okay, so if it's primary the H stretching, okay, so should show two peaks, okay. So if you secondary amide, okay, you should see kind of only one peak, okay. So that's how do you distinguish kind of from other compounds, okay. So those peaks are normally kind of quite sharp, okay. So not so broad as the OH, okay. Ester, okay, so ester in addition to sealed bond stretching, okay, you should see kind of the CO single bond stretching, okay, so about 1200, okay, so especially kind of sp2 CO single bond stretching, okay, very strong kind of signals, okay, so and then come to the acid anhydride. Acid anhydride, okay, normally only show will show kind of two sealed bond stretching, okay. So that's very unique. All other the carbonyl compound, okay, only show one peak, okay. So the one sealed bond stretching, okay. So that's you can use the whether there are two peaks in the carbonyl area, okay. So distinguish kind of acid anhydride from others, okay. And nitric compound, we just learn kind of the symmetry bond stretching 2200 to 2300, okay. So those help us kind of distinguish all the carbonyl compound, okay. All right, okay. Here a little bit summary of the strengths and also limitation of the IR spectroscopy, okay. So IR, okay, so connote the used to determine the molecular structure, okay, So especially some kind of we call kind of the isomers, okay. So that's the IR, it's hard to figure out, okay. IR can provide information about the function group, okay, but hard to kind of figure out the structures, okay. But NMR, okay, so chapter 14 will kind of figure out the structure, okay, so pretty useful, okay. And then some the signals can maybe the ambiguous, okay. So give you one example, okay. Right. So for example, for the arcane CC bond kind of stretching, okay, 1675 to 1600, okay, and then for the amide case, the sealed bond stretching is 1617 to 1600, okay. So very close kind of the absorption area, okay. So that's hard kind of hard to distinguish, okay. This belongs kind of the CC bond or belongs kind of sealed bond, okay. So. And the functional group, okay, so can be indicated by the IR, okay, so that's already said, okay. And one thing can be true, okay, so if there's so we already know that kind of if it shows some kind of signal in area, okay, so we cannot see the kind of belong to certain functional group, but in certain area, if there's no signals, okay, so definitely kind of prove there's no such functional group in this molecule, okay. For example, if you didn't see any kind of carbonyl kind of the absorption around like the 1700K to 1800, a little bit lower maybe to 1600K, and then that means there's no carbonyl functional group in this molecule, okay. So that's pretty safe, okay. So there's no such peaks, okay. So that means no such functional group, okay. So and so IR kind of another useful application kind of help to identify some unknown samples, okay, because each compound it should have a very unique IR spectrum, okay, so different from other compound, okay, and that's we already learned that kind of because they are fingerprint region, okay, and so for example, okay, so if you find some kind of unknown samples, okay, and take it as IR, okay, and you search here the IR database, okay, so there's a lot of IR database online, okay, and you find another compound that shows exactly same IR spectrum, okay, so that means these two actually 99% will be same compound, okay. All right. Okay, and then there's one important thing, okay, so yeah, please write down, okay. So yeah, IR you not only try to memorize try to look at its frequency, okay. So also need to look at kind of its the peak shifts and also intensity, okay. So yeah, so write it down, okay. That's kind of quite often missed by some kind of beginner, okay. So yeah, students, okay. So yeah, the value for the intensity, okay. So yeah, that's here the weak, medium, strong, okay. Weak, medium, strong, okay. So that's here 3, okay. All right. So yeah, quite often for some kind of beginner, okay, like you guys, okay. So just look at the frequency, okay. So yeah, and then that's gonna determine this kind of that's here the signal or not, okay. But here the shapes and the intensity can provide a lot of information, okay. For example, we just learned the arc, okay, and also capacity, okay. All of them show the peak OH stretching, okay. So yeah, centered around the kind of maybe the 31, 3200, okay. And but for the OH group peak, okay, so that's kind of the much kind of the symmetrical, okay, and also the very nice kind of the rounded kind of tips, okay. But for the okay, so yeah, OH, okay, so pretty much like this, okay. And then the region, okay, so for the OH, okay, so never go beyond kind of 3000, okay. But for the capacity, okay, so for capacity, okay, so that's the much broader, okay, so yeah. So that's the normally the OH stretching, okay, so like this, okay. But for the capacity, okay, so that's much broader, okay, and also much less unsymmetrical, okay, so that's capacity kind of 2400 to 3500, okay, so that's we can figure out, okay, so yeah. Okay, so now we bring back this table, okay. Right, can you guys see the table?
Yes.
Okay, so yeah, just keep in mind, okay. And another thing, another example is remember I just give example, okay. So for the arcane kind of C double stretching, okay, 1675 to 1600, okay. A might okay, so yeah, the C double stretching 1670 to 1600, okay. So we're similar kind of positions, okay. But you can use the intensity, okay. So yeah. For the arcane kind of peak, normally I will say kind of the weak to medium, okay. So but for the A minor kind of seal down strategy will be strong, okay. So by that you can distinguish these two the different compound, okay. So that's please keep in mind, okay. So yeah, in shapes and also intensities, okay. All right. And some people said kind of do we need to memorize all this kind of the frequency, okay? So yeah, showed in kind of table, okay. The answer is no, okay. So no, okay. So I already uploaded this table on EduCAD, okay. So you can print out this table, print it with you for the future exam quiz, okay. So yeah, for the future exam quiz, okay. So this you don't need kind of memorize, but the little bit keep idea, okay. So what kind of the absorption showed what kind of area, okay. So little bit keep idea, that you will save a lot of time, okay. All right, and here, okay. So we'll show you how to use this IR table to solve the questions, okay. And also show you kind of what's common question. Can you see the maybe chapter 5 or maybe the quiz exam in quiz 5 or maybe in the exam 3, okay. All right, first type question case showed like this, okay. So give you two compound, ask kind of how do you use IR spectrum, okay, and which area as IR spectrum, okay, can be used to distinguish these two compound, okay. So those type of questions can kind of first thing you need to do is kind of find what's functional group in these two molecules, okay. For the last molecule, okay, so you have ether, aromatic compound, and also catalytic, okay. For the right molecule, okay, so you have aromatic compound, ether, and also tertiary amine, okay. So definitely we cannot use the ether and also aromatic compound distinguish these two compounds, okay. So because there's both show these signals, okay. So for tertiary amine, okay, so there's no IR spectrum, okay. So only thing left can be used to distinguish the compound carboxylic acid, okay. So carboxylic acid, okay, and then look at kind of IR, okay. So what's carboxylic acid absorption, okay? So 3,400 to 2,400, okay, and also carbonyl absorption, okay. And then you look at kind of the options, okay. So you find kind of D, okay, overlap with the OH stretching of carboxylic acid, okay. So that's D is the right answer, okay. 2,400 to 3,500, okay. So that's how do you finish these questions, okay? Use the IR table, okay. All right, and then we move to a little bit harder one, okay. So I call this type of question called the matching question, okay. So normally give you one IR spectrum, okay, and then give you a bunch of candidate molecule, okay. Ask you which of this molecule give the IR spectrum below, okay. All right, and so you guys can take a try, okay. So give you 1 minute, okay. And for the let me see, okay. So so for the IR information, need for this spectrum kind of all showed in here, okay. So you don't need kind of look at the other IR spectrum, okay. Take a try, okay. And I'm also going to show you guys kind of later, okay. So how do I solve these kind of questions, okay. All right. So if you know the answer, okay. So you can either turn the annotation, okay, just circle the answer, okay. Otherwise, you can also type in the answer in the chart window, okay. So let's label the 1, 2, 3, 4, 5, okay. So that's gonna do it, okay. This morning class, okay, no student know the answer, okay. Let's try this afternoon, okay. So all the necessary kind of the IR spectrum all showed here, okay. All right. Anyone know what's which molecule match the bottom IR spectrum? Wow, perfect, okay. That's the right answer. Okay, pretty good, okay. That's better than this morning. The morning student, none of them students know what's the right answer, okay. All right, okay. So for the IR spectrum, okay, so once you have one IR spectrum at hand, okay, the first you need to kind of look at is any peak around like 1700, okay. So that's the most useful information can be provided by IR, okay. So that's tell you whether kind of a carbonyl conformation will be in the molecule, okay. So for this one, okay, so look at here, okay, 1700, okay, so this area, okay, pretty much nothing, okay, 1700, okay, so 1700 here, okay. So that means there's no carbonyl group, okay. So that means cannot be this one, okay. So because the carboxylic acid has kind of carbonyl group, okay. Right, and then next kind of you look at what's the major peak in this IR spectrum, okay. And clearly you see this kind of very nice, beautiful peak, okay, very symmetrical, okay. So from maybe 3,000 to 35, 3,600, okay. So that's typical alcohol peak, okay, OH, okay. So all right, okay. So that means this compound has to be kind of alcohol, okay. So then quickly we shrink the answer to these two, okay. All right, and then we see what's different kind of between these two compounds. Okay, we find kind of first one, there's just saturated kind of city single bond, okay. Second one, there's kind of city double bond, okay, alkene, okay. So then you look at the alkene, okay. So alkene, you should see some kind of CC double bond stretching around like 1640, 1670 something, okay. And also the sp2 CH stretching, okay. That's above 3,000, okay. All right, so you look at the spectrum, okay. About the 1600 something, okay. So that's you draw here. Pretty much nothing, okay. And then you look at kind of is any peak above kind of 3,000, okay. So looks like only alcohol, okay. All the peak, so for the CH stretching, okay, below 3,000, okay. So definitely there's no CO double bond, C double bond kind of stretching, okay. So no, also no sp2 CH, okay. So that's only possibility kind of the two, okay. All right, pretty good. Okay, so that's how do you answer these kind of questions, okay. All right, and then we move to the last one, okay? So this is pretty much the most difficult question you'll see in the for IR chapter, okay? So this type question can give you one IR spectrum, okay, and then give you one formula, okay? Ask kind of figure out its structure or its functional group, okay? All right. So if you have this kind of questions, okay, the first thing you need to do is calculate DU number, okay? So okay, based on formula, okay, right? You guys kind of take a try, okay? So and then type in the chart window, okay, what's the degree of saturation for this molecule, okay? One, okay, so that's pretty fast, okay. That's also better than this morning, okay. So this morning the students all forgot how to do the degree of saturation, okay. So that's don't forget some kind of your old knowledge, okay. So degree of saturation, okay, remember equals 2, okay, 2 times carbon number, okay, plus 2 minus hydrogen number, okay, minus the hydrogen number plus nitrogen number, okay, and the whole thing divided by 2, okay, right, and then we have the 4 carbons, okay, 2 times 4, okay, plus 2 minus 8 hydrogen, okay, so no oxygen, no hydrogen, nitrogen, whatever, okay, the whole thing divided by 2, okay, so that's give you 1, okay. So that means for this molecule, okay, so we have 1 degree of saturation, okay, either 1 ring or 1 double bond, okay, right. Okay, and then following thing, okay, like I said, okay, the first thing you need to look at kind of for IR, okay, is any peak around like 1800, okay, so we still bring the IR chart back. Right. Around like 1700, okay, so not sure whether kind of a carbonyl group in this molecule, okay, all right, so now you can see here, this guy. Okay, some peak around like 1700, okay, so by the way, okay, so if you work on some IR spectrum, okay, so maybe you can bring a ruler, okay, so that's help you kind of read the wave numbers, okay, right, so that means this molecule should have a delta bond, okay, so right, but we already learned there are a lot of the compound has a carbonyl group, okay, so how do we tell which compound it is, okay? So that's the important thing, okay, here, okay, so don't forget the formula, okay? Look at your formula, okay, so that's the quite the common, some kind of the kind of important tips for you guys, okay? So the formula actually kind of provide a lot of information, okay? So formula, carbon, hydrogen, okay? And then one oxygen, okay? And so if you look at the IR table, okay? Actually kind of let's just go here, okay? So if it's the capacity, okay? So you should see kind of 2 oxygen, okay? 2 oxygen, okay? So if it's ester, okay, you should also get 2 oxygen, okay? And if it's amide, okay, so amide should have kind of nitrogen. This one has no nitrogen, okay? So if it's the acid chloride, you should kind of chloride in the formula, okay? And if it's the acid anhydride, there are 3 kind of the oxygen, definitely not anhydride, okay? And then only 2 kinds of compound have the only 1 oxygen, 1 ketone, 1 aldehyde, okay? So that's greatly shrink down kind of the possible compound, possible structure for this molecule, possible kind of functional, okay? All right, so ketone, aldehyde both have only 1 oxygen, okay? So now question for you guys, okay? Is this compound ketone or aldehyde, okay? Yeah, anyone know it, okay? Type his answer in the chat window. Or someone said ketone, okay? Any other choice? Okay, so both ketone aldehyde showed carbonyl, the absorption, okay? So here, okay, so that's here the maybe it on the annotation. Pretty similar, okay? So that means carbonyl, okay, this peak cannot distinguish, okay. But for the aldehyde, okay, so aldehyde has a very special kind of two peaks we just learned, okay. So for the CH stretching aldehyde group, okay. So one kind of the 2850, another kind of 2750, okay. Right, so you then look at here. Okay, so that's these two peaks. Okay. So normally, no other CH stretching shows so low kind of stretching, okay. So so low kind of the CH stretching, okay. So only aldehyde can show it, okay. So that means this compound actually is aldehyde, okay. So aldehyde case. Yeah. So actually, this compound actually from benzaldehyde, okay. So the real structure is not benzaldehyde, so kind of butanol, okay. Yeah, that's actually the structure, okay. So, okay, so here we down to the chapter 13, okay. Anyone have any questions? All right. Okay, so later today I will give out kind of chapter 13 homework assignment, okay, and also tomorrow, okay, so we'll do some practice, okay, so for the IR chapter, okay, help you guys prepare the coming and the quiz, okay, that's quiz 5, okay, quiz 5 only cover chapter 13, okay, the IR chapter. All right. Any questions? So if there's no further questions, okay, so we'll start a new chapter, okay? All right, so also get a new page. Okay, so the new chapter called nucleus magnetic resonance spectroscopy, okay? So the abbreviation is NMR spectroscopy, okay? So this is the also another huge chapters, okay? Also very hard chapter, okay? So in organic chemistry 1, okay, so we have two tough chapters. One is the chapter 7, stereochemistry, okay? Another one is NMR chapter, okay? And so we'll spend probably more than 1 week, okay? Actually kind of probably 2 weeks, because next Wednesday there's no class, okay? So we'll study this chapter, okay? So and so NMR actually kind of very useful tool for the organic chemistry, okay? So and actually nowadays, okay, so for organic chemistry, so no one use IR, okay, pretty much, okay. So but the NMR kind of the fundamental tool for the organic chemistry, okay. So it help kind of figure out the structures, okay, give a lot of information, okay. All right, okay. So now let's start, okay. So for NMR, okay, so the abbreviation kind of NMR, okay. So the nucleus magnetic resonance, okay. So that's the study the interaction of the atom, also nucleus, okay. So with the radio frequency. Radio frequency, okay, we know that kind of very long kind of wavelength, and then very kind of low frequency, okay, and then low energy, okay. So this energy too low, okay, only can change the spin direction of the nucleus, okay. So and provide information about the number and also types of atom in one molecule, okay. So there are a lot of the atom can show the NMR spectrum, okay. So but in organic chemistry 1, okay, so we only study kind of the proton NMR and those carbon NMR, okay. So H1 means kind of proton, okay, that's the one of the isotope of hydrogen, okay. And then C13 is also one isotope of the carbon, okay. So C12, okay, so most bonded, not NMR active, okay. And provide information about spectrum and also the structure information, okay. And here just little bit talk about the very kind of rough the general idea about what happened for the NMR, okay. So a little bit of theory, okay. Here, okay, so the energy gap, okay, so ground state and then excited state, okay. So and then normally speaking, kind of for the nuclear, okay, so nuclear has its spin, okay, only stay at kind of ground state, okay, so because they are lower energy, okay. And then there's kind of energy gap between the ground state and those excited state. Okay. All right. So if this the spin, okay, should align with external magnetic field, okay. So that's XT, okay. So BXT is kind of external magnetic field, okay. So same direction, okay. And then if you strike here the nucleus with some radio frequency, okay. So if this radio frequency kind of energy match with the energy gap between the ground state and also excited state, okay. and then that's yeah, this nucleus, okay, so we will yeah, jump into yeah, excited state, okay, and then this process will involve kind of we call the spin flip, okay, the change the direction, okay, so from the same direction as the electromagnetic field to the opposite direction, okay, from magnetic field, okay, so like this. Okay. All right, and so yeah, normally when you give the radio frequency, okay, just kind of by a pulse, okay, so yeah, just the pulse, okay, just like this. And then once you stop the radio frequency, okay, and then because this is the no at excited state, okay, so not so stable, okay, so want to go back to the ground state, okay, so that let's go back to ground state, okay, if you release some the radio frequency, okay. So this radio frequency may be a different energy from the original radio frequency, okay. So I use the delta E pi, okay, and also the energy different frequency also different. I use mu pi, okay. All right, and then this release the radio frequency can be detected by NMR instrument, okay, and then you see kind of NMR signal, okay. Something like this, okay. So clearly see you kind of NMR spectrum actually belongs to kind of emission spectroscopy, okay. Okay, emission, okay, so because you release some the electromagnetic radiation, okay. All right, okay. And here just keep in mind, okay, so note all the atom or kind of nucleus will be give NMR signals, okay. So only NMR active nucleus give kind of signal, okay. So yeah, here we already done kind of this NMR active atom should have kind of spin, okay. So yeah, spin quantum number cannot be 0, okay. So then they can give kind of the absorbed radio frequency and give out the kind of NMR signals, okay. So what kind of atom is atom NMR active atom, or we can say kind of have spin, okay. So that's showed here, okay. So this atom has O number of proton or O number of neutron or both, okay. Then we will have kind of nucleus spin, okay. So normally I just show you kind of this chart, okay. So help you understand, okay. So for example, you have kind of all the proton number, okay, and even proton number, okay, or maybe all the neutron number, okay, or kind of even neutron number, okay. Yeah, so those neutron and those the electron kind of two proton kind of two component in the nucleus, okay. All right, okay. So if the both neutron and those the proton number are O number, okay, so that will be NMR active, okay. So if it's the old neutron number and even proton number, also NMR active, okay. So if it's the even neutron and all the protons, okay, so that's also NMR active, okay. Only the even neutron and also all the proton, even proton, even neutron, even proton, okay, that will be NMR inactive molecule, okay, inactive atoms, okay. So here kind of show you some example for the NMR active nucleus, okay. So like protons, okay, H1, and also this is the we call deuterium, okay. So that's the H2, okay. So another the isotope of the proton, okay. And then carbon 13, okay. Someone asked now why the note carbon 12, okay. So carbon 12 is the most abundant the carbon isotope, okay. But unfortunately, okay, both it's kind of the proton and also neutron, okay, are even number, okay. So 6 proton, 6 neutron, okay. So that means carbon 12 actually kind of NMR inactive, okay. And then if it's kind of carbon 13, okay, although it's proton number, okay, proton number 6, but neutron number is kind of 7, okay. So that's here, okay. So neutron numbers old, okay, proton number kind of the even, okay. So that's still NMR active, okay. And then same thing for the oxygen, 16, okay. So that's also most abundant the oxygen atom, okay. So both neutral number and also the proton number, okay, are odd number, even number, okay, so yeah, both are 8, okay, so that's here that means here oxygen 16 is actually kind of yeah, NMR inactive, okay. And some other common NMR active nucleus showed here, okay, so yeah, the nitrogen 15, P31, and also phosphorus 19. Okay. Some last question. Carbon 14, okay, so carbon 14, yeah, that's right, okay, carbon 14 also NMR inactive, okay, so yeah, inactive, okay, so because the carbon 14, 6 protons, okay, and then 8 neutral, okay, that's NMR inactive, okay. So yeah, different nucleus has the different have different kind of spin, okay, so yeah, carbon and also proton and also carbon 13, okay, so only has the 2 spin kind of the direction, okay, so yeah, plus the half and the minus half, okay. Right, and here a little bit about the NMR the theory, okay, so yeah. So yeah, it's much more detailed than I explained, okay, so that's just kind of very general kind of information, okay. So yeah, if it's NMR active nucleus, okay, NMR active nucleus, okay, so it will have kind of spin charge, okay, so yeah, and then it generates the associated magnetic field, okay, so we call kind of magnetic moment, okay, so that's maybe show you, okay. So yeah, one nucleus, okay, so there's a lot of proton inside, okay. Yeah. And this proton kind of just circulate around the nucleus, okay, just in the nucleus, okay. Right. So for example, in this direction, okay. And then once kind of circulate this way, okay, so we will generate only magnetic field, okay. So and then show kind of magnetic kind of the moment, okay, like this, okay. So that's this is the magnetic moment, okay. Yeah, here. And so normally situation, okay, so for the nucleus case, this magnetic moment, okay, can be any direction, randomized, okay, so show that like here, okay. And but if there are some kind of the external magnetic field, okay, applied, okay, external magnetic field, okay, so if we show the kind of these directions, okay, and then we'll align the nucleus, okay, so magnetic field, okay, in 2 directions, okay. One direction, okay, same direction as the external magnetic field, okay, so going same direction. So this one we call kind of the ground state, okay. Another just the opposite direction from external magnetic field, okay. So that's shown here, okay. So you can see kind of the opposite one has kind of higher energy than the same directions, okay. So this one will be called the kind of the excited state, okay. And then also we call the ground state as alpha state, and the excited state as kind of beta state. Okay? That's kind of energy gap between these 2 guys, okay. Because the excited state has kind of the higher energy, that has less population, okay. So kind of different quality. More nucleus stay at kind of ground state, okay. All right, and then so that's alpha state and the beta state, okay, and also the energy gap, okay, so delta G, okay, delta E, okay. And then if you strike a sample with some the radio frequency, okay, so also called kind of photon, okay, so and the excited one nucleus maybe more, okay, so from ground state into the excited state, okay, beta state, okay, and then during this process, okay, so the spin of the nucleus will change, okay, so go to kind of opposite direction. That's we call it the spin flip, okay. And then if you continue the strike, okay, so that's the 2 states kind of get saturated, okay, so just kind of 2 same populations, okay. But if you take off stop the radio frequency, okay, so because the ground excited is kind of not stable, okay, so the nucleus don't want to stay at kind of excited state, okay, so go back to its the ground state, okay, also called the alpha state, okay, and then this process will release radio frequency, okay. This radio frequency will be recorded by NMR instrument, okay, and then show you NMR signals, okay. Here just kind of a little bit the idea, okay. So for you guys, don't need get kind of too detailed, okay. So just a little bit idea, okay, what's going on for the NMR, okay. So all right. So in the end of the class, okay. So just the one formula, okay. So tell you the what's influence of external magnetic field, okay, and also the different nucleus show different the NMR spectrum, okay, different kind of the frequency, okay. So that's all come to this equation, okay. So delta E is kind of here the energy gap between the alpha state and also here the ground state, okay. And then H mu, okay, so that's mu is here the radio frequency, okay. H is kind of here the Planck constant, okay, equals to the H is still Planck constant, okay, and then gamma, okay, divided by the 2 pi, okay, and then the whole thing times here the let's see, we call the external magnetic field, okay, strength, okay. So that's the B, okay. All right, so this one, okay, gamma we call it germagnetic ratio, okay. So this one is only related to the individual atom, okay. So nucleus, okay. So different atom has different kind of gamma value, okay. So here's kind of external magnetic field, okay. Yeah, this external magnetic field is strong, okay. So you can see kind of the higher external magnetic field, okay, and then higher energy, okay, and also this also plays some kind of important, okay. All right, okay. So it's already 1:51, okay. So we stop the class today here, okay. All right. Do you guys have any questions?